Okay, 2.7 is solving counting problems that involve permutations and combinations. And so how do we know when to use what? So let's look at some problems. But before we get started with that, remember the difference between a permutation is when we're dealing with like sequences or actually arranging objects. So order matters. Order matters. Whereas a combination is when we're just grouping together how many combinations, so order does not matter. And both of these assume no repeats. Okay? If we have a problem with repeats, that's when we use fundamental counting principle. Okay, so there are 5 swimmers in the first heat of a race. Jordan, Taylor, Ryan, Neil, and Justin. How many ways the 5 swimmers finish first, second, and third? So here we have very distinct positions. Okay, we have first position, second position, and third. And if this was the Olympics, right, it matters where you finish. First and second gives you a totally different, you might be like world famous if you get first and forgotten about if you're second. So position matters. So in a position like this, in a situation where our positions matter, then order matters. And if it's order matters, then it's a permutation. Now permutation we can solve with fundamental counting principle as well, or we can use the calculator. So if I want to use first fundamental counting principle, I think, okay, how many people do I have to choose or pick from for the first position? And we have 5. There's 5 people. For the second, now that we've already put somebody in first, there's 4 and 3. So notice how neither of these people can get first, second, and third. That's kind of assumed in permutations and combinations, that there's no repeats. So that gives us 60. We could have also solved this with, we have 5 people, and we want to pick 3 of them and order them in their positions. And so that also gives permutation because order matters. Now, how many ways can the 5 swimmers qualify? For the first race, it's a top 3 finishers qualify. So in this situation, order doesn't matter. As long as I get first, second, or third, I qualify. So it really doesn't matter as long as I'm in that group. Order doesn't matter. And so if order doesn't matter, that would be a combination. We have 5 people. We want to choose 3 of them. How many ways can we take 5 and choose 3? Remember the formula is 5 factorial over 5 minus 3, so 2 factorial, and then divided by our r factorial. So I could write this as, just to review, 5 times 4 times 3 factorial over 2 factorial, 3 factorial, and the 3 factorials would cancel. So we're really left with 5 times 4 divided by 2, or 10. 10 combinations. So what's the key idea? When solving these counting problems, you need to determine if order plays a role. Does order matter? And then you can decide if it does or doesn't, whether it's a permutation or a combination. Things to remember. Once you establish whether a problem involves permutations or combinations, you can also use these strategies. Look for conditions. Are there any restrictions? Consider these first as you develop your solution, right? Does somebody have to go first? Or does somebody have to be last? Those are very important and should be dealt with right away. If there's a repetition of r of the n objects, it's eliminated by dividing by r factorial. Okay? Remember, and is when we can apply the fundamental counting principle. We multiply, right? We multiply them. Whereas if we see or, we cannot use fundamental counting principle. We have to add, right? So when it's an or situation is often when there's different cases. And we looked at some examples yesterday. So an example of that is when you see like at most or at least, at most people, so out of 3. So 2 or 3, or 1, 0, 1 or 2. 0, 1 or 2 would be at most, or at least 2, right? So those are situations where you different. And so we solve each case and then add them together. So let's look at an example. Identify where whether each situation involves a perm or a com and explain how you would know. Choosing 3 toppings for a pizza of 25 different possibilities. Now, does order matter when you put the toppings on? No, order doesn't matter. Pepperoni mushroom pizza is still a pepperoni pizza, whether you put the pepperonis and then the mushrooms on, or you put mushrooms and then pepperoni, right? It's hot pepperoni mushroom and cheese, of course. So order does not matter. And so if it doesn't matter, then it's a combination. So we have 25 options, and we want to choose 3 of them. That would be a combination. Perms and combs this unit. It's all about perms and combs. Okay, choose a CEO, president and vice president. Of 20 candidates. Now, does the order matter? Whenever we have specific positions, that means order matters. You might be livid if you're vice president and you wanted the president, right? President has different privileges than the vice president. So that would be a situation that is a permutation. It's a perm. So 20, and we want to pick 3. The number of outcomes possible when rolling 3 die, 1 red, 1 blue, and 1 white. So the key here is that distinguish which die is which color. There are 3 different die. 3 different die. Right? And the key here is that so if I have like a 1 red, 2 in the blue, that's have a white, 3 in black, that would be different than 3 red, maybe 1 blue, a 2 black. Key here is different colors, whereas, yeah, so we have different colors, so 3 different die order matters. One is kind of unique because you would this first die, you have 6 choices. You have to think about all the different outcomes. So you can roll a 1 through 6. So that's 6 options. So you actually wouldn't, yeah, I don't really like this one because you fundamental counting principle. Because numbers of outcomes for the first color, 6 for the second, and 6 for the third. Okay, so although order matters, which is permutation, the key here is that they're different colors, right? So technically you can have a repeat. You 3 6s in a row, so because they're different colors. So this would be a fundamental counting. Determine the number of ways 5 children from a group of 11 can start in a game of pickup basketball. So if we're just grouping them together, group of 11 start in a game. We're not putting them in specific position. Order does not matter. That's a combination. So we have 11, choose 5. All right, next page. A piano teacher and her students are having a group photo taken. There are 3 boys and the piano teacher, we have the piano have 3 boys. There's a total of 9 people in this photo. The photograph wants the boys to sit together and the girls to sit together for one of the poses. How many ways can the student and teacher sit in a row of 9 chairs for these poses? Now, first off, we need to establish, does order matter here? Okay, order does matter. There's a few ways we can set this up. You can think of it as 5. So they're together, the 5 girls. And then okay. So one way we can think about, first of all, how many ways can we arrange the girls? So you can either, we know it's a permutation, or so there's 2 ways you can input it. You can go 5p5. So this could either be 5p5 or 5, 4, 3, 2, 1, which is 5 factorial. Right? We're arranging the girls because they're different girls. The boys, it's the same thing as 3 boys. We want to arrange all 3 of them. 3, 2, 1, which is 3 factorial. And then the teacher, well, there's only one teacher, 1 factorial, or 1. Just arranging them in their individual groups. Objects, the girl, boy, teacher, right? How many ways can I arrange the girl, boy? And there's 3 factorial ways, right? If we want to arrange n objects, it's n ways. And there's we want to arrange, so there would be times 3 factorial. Because there's 3 factorial ways to arrange the girls, the boy, and the teacher, right? You can go girls, boy, teacher, girl, teacher, boys. We can go teacher, boy, girl, or teacher, girl, boy. Right? You can list the rest. There's a couple ways you can enter that, right? So arranging I think the easiest is the bottom. 5 factorial ways of arranging the girls. 3 factorial ways of arranging just the boys inside their set. 1 factorial ways of arranging the teacher and her subset. And then these sets, there's 3 factorial to arrange girl, boy. Grabbing your calculator, let's see here. Okay. Math, left arrow 4 factorial times 3 factorial. Now 1 factorial, 1 is 1, so you don't have to enter that, times 3 factorial gives us a total of 4,320 arrangements. Combination problems are common in computer sciences. Suppose there's a set of 10 different data items represented by A, B, C, D, E, F, G, H, I, J. So right away, I'm just going to count. 10 different letters to be placed in 4 different memory cells in a computer. Only 3 data items are to be placed in the first cell. We only want 3 items. Second cell, we're going to have 4 data items. The third cell, we want 2 items and 1 item in the last. How many ways can the 10 data items be placed in the 4 memory cells? So inside this, we're talking about a combination problem, okay? Inside the cells, the order does not matter. So it's a combination. So we start with the first, okay? In the very beginning, when we first want to put four of these letters, we have a total of 10 different, and we want to choose 4, or sorry, choose, there's 3 items, because order doesn't matter. Now that we place 3, how many do we have left over? We have 7 left over. So for the second cell, now that I've already placed 3 of them, there's 7 left, and we want to choose 4. And the last item, or second item, now that we've just placed 4 more, so 7 have been used up, we have 3 items left. I want to choose 2 of those to go in the third, and now I have only 1, and I want to choose 1. Okay? Calculator. Okay, so we can type that in all at once. 10, math, left arrow 3, so 10 choose 3 times 7 math, left arrow 3, 7 choose 4 times 3 math, 3 choose 2, or you can figure out what they all equal individually. 1 choose 1 is 1. So you type it in all at once. I'll just show you that. And this one doesn't change it. There's one way to arrange one object, or choose one object. So 1,260 ways. Sorry, 12,600 ways. Okay, I'd like to give you one more example. Five card hands. Can be made with most 2 red cards. So at most 2 red cards. So situation, we have a case. We have case 1 and 2 red cards, so we can have 1 or 2, 0, 1, or 2 red cards at most. So if we have 0 red, then we have 5 black is one case. Case 2, 1 red and 4 black. Case 3 would be 2 red and 3 black. So we want to solve them individually and add them together. This is a or situation in between case 1 or case 2 or case 3. Solve them individually and then add them together. Do this all at once. So in case we said 5, I don't have to choose. I can just go straight because we don't want any red. You can 26 different cards, choose 0, but we can go straight to just the black. So 26, choose 5 black would be the first case. The second case, reds, we want to choose one of them. Red and black, so that's multiplication. And 4 black. 26, choose 4. And the last case would be 26, choose 2 reds, and then 26 blacks, we want to choose 3 of them. To your calculator. So one at a time if you like. 26, math, choose 5, 65,780 for case 1 plus 26, choose 1 times 26, choose 4, 388,700, and then 2 red. So easy second, enter, and just go back for 2 red and 3 black. 845,000. When we add these all together, we get 1,299,480 combinations. Okay, so your homework is page 45 in your workbook, numbers 1 to 6 and 8 to 10. So MIT number 7. MIT number 7.